Okay. So let's do another example here of finding zeros and identifying their multiplicity. So this is an example from MathXL. Find the zeros of the polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. First thing I want to mention about a problem like this is, even though it doesn't ask for it, let's talk about the degree. Okay, to clear up maybe some confusion there. When we are finding the degree of a function, we're supposed to be finding the highest exponent of x, right? And if you look at a problem like this and you identify that this is squared right here, that might be your first reflex, is seeing the squared and saying, well, that's the highest exponent, so it has to be 2. But really, if we expand this entire expression or this entire function, and we get rid of that exponent by writing the x plus 4 twice, take a look at this function. Now, we're not going to do it, but if we did FOIL and distribute all of this huge mess, right, the first thing we'd do is probably FOIL these two together, and we'd have x squared, blah, 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 right? But then I'd have to multiply that times this third binomial, which would be x squared times x, blah, 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 and a bunch of x squared x terms and whatnot. Okay, and then as we clean that up, the highest exponent of x then would be q. And when you confronted with a problem like this, you can count your exponents like this, because you know this is going to end up being an x squared, and then there's an x to the first here for an overall degree of 3. Okay, and then as far as the leading coefficient is concerned, if I did multiply all of these x's in the front of each binomial, that'd be x cubed, and then that would have to be multiplied by 9. So we have a positive leading coefficient. And remember that when we look at the degree and the leading coefficient together, those give us the end behavior of this function. Okay, so just wanted to put that out there just to kind of clear things up. If you're ever asked to identify the degree, don't just jump immediately to the first exponent that you see. Okay, when you have the general form like so, where it's not in factored form, when it's written like this, you can say, yeah, the degree here is 3. But when they're writing the factors like so, kind of have to think about what that would look like if we multiplied and distributed, FOILed everything together there. Okay, so getting back to it, the zeros, if we set this equal to 0, and then we take all of our factors and set them equal to 0, okay, we would say, well, we're not going to say 9 equals 0, even though this is a zero product property the way this is set up. We wouldn't say that 9 equals 0, right? Because 9 can't equal 0. But we would say that x plus 5 equals 0. And we would say here, x plus 4 equals 0. I'm not going to write that twice. It's be the exact same statement. I'm just going to identify the fact that when I solve this one, that negative 4 has even multiplicity, okay? Because there are 2 of these factors. So we have even multiplicity, and when there's even multiplicity, we know that the graph is going to bounce at negative 4. Over here, coming back to this one, we subtract 5 from both sides. We see that this only happens from this one factor. So this has an odd multiplicity, or a multiplicity of just 1. Okay, and when you have odd multiplicity, you're going to cross. The graph is going to cross at that value. Okay, so if I started to put together a graph, and I know it's not a part of this problem, but if I wanted to challenge myself here without a calculator, I have one of my zeros at negative 5. Let's put that there. My other zero is at negative 4, or zeros, should I say, right? Because it counts twice. Okay. We established that the degree here is 3. So we should have 3 solutions. Those 3 solutions are negative 5, negative 4, and negative 4, right? Because the degree is 3 and the leading coefficient is positive, okay, we know that the end behavior is falling to the left and rising to the right. So when we look at these 2 zeros, and these are the only 2 zeros for the function, the leftmost 0 is going to be the last time we intersect that x-axis. So the end behavior that is down and to the left has to come from that leftmost 0. And the end behavior that's up and to the right, or rising, we know has to come from the rightmost 0. So if I'm sketching this graph out, I know these 2 behaviors have to exist based on degree and leading coefficient. Now, when we talk about the graph crossing at negative 5, that was this 0 right here. The graph is going to cross at that point. But at some point, it has to turn back down and come and hit this 4 or -4. So I'm going to have to bring it back down and hit -4. Now, on the right side of 4, I know that it has to go up and to the right, and we know that it has to bounce. So we're probably looking at a graph that looks something like this. Okay, that's using degree, leading coefficient, the x-intercepts or the zeros, and their multiplicity to kind of come up with a graph, just a sketch of what this polynomial function looks like.